Hi, this is Kenneth Corrigan again, and today I'll be presenting sections 5 and 6 from Chapter 8, which are high performance computing as well as visualization. Okay, so for just a quick introduction, scientific research generally requires computer-made models and simulations, and these can involve extremely complex calculations. Now, these complex calculations call for the use of supercomputers, such as the system seen above, which is cleverly named the Titan. Supercomputers achieve the speed and power necessary through two parallel processing techniques, which are called centralized and distributed processing, and we will explore the details of both of these. So, parallel processing. Parallel processing involves using one or more computers to work on the same task at the same time, hence the name parallel. This technique allows the work to be completed more quickly, and this can make a tremendous difference in speed. And to illustrate this difference in speed, I have provided these two graphs. The top graph represents a processing technique in which the tasks can only be completed one at a time. So you see, as processor 1 completes the first task, processor 2 has to wait for that first task to be completed before it can start to complete its second, and so on and so forth to the 10th. While the bottom graph represents a parallel processing technique. The top technique essentially takes 10 times as long, as each process must be completed before the next can be started, whereas the parallel process on the bottom allows each to be completed at the same time, thus saving a lot of time. Okay, so centralized processing. This technique, centralized processing, involves multiple processors installed in the same computer system, and these processors can number into the tens or hundreds of thousands, depending on the productivity desired. Many PCs feature centralized processing, such as the dual-core and quad-core systems. Additionally, classic supercomputers utilize centralized processing, which is why they took up huge amounts of space. If you remember back to relatively old movies in which there are many computers, many processors in one room. That's basically the gist of it. Shown here, though, is a modern example of centralized processing, and this is called the IBM Blue Gene series. You can see the name right there. And this series can have up to 300,000 processor cores and fill a large room. Okay, so distributed processing. A different approach compared to centralized processing in parallel processing is the use of distributed processing. Distributed processing uses multiple separate computers connected by a network rather than one specialized computer. The connected computers can take the form of desktops or laptops, as well as mainframes and supercomputers, and they are generally distributed across a wide geographical area. This technique works by sending a separate part of the task to each connected computer, which that connected computer processes independently and then sends back to a central computer. And the picture here illustrates this technique with the double pointing arrows, representing the task being sent out and the completed task being sent back. Obviously, the main computer is the red one there, which is sending out and receiving the data. Distributed processing is very scalable, as computers can be added or removed easily, and it is a lot more efficient. So an example of a distributed processing project is SETI at home. SETI stands for the Search for Extraterrestrial Intelligence, and this search is done by collecting radio signals from space and storing them at UC Berkeley. And UC Berkeley runs this program. Volunteers use this special software to download a small part of the signals and analyze them automatically, and then proceed to send the results back to Berkeley. Without the volunteers and this distributed processing system, the volume of data would be too great for UC Berkeley to handle, and too expensive as well. There are several million active users, which makes it the largest distributed processing project ever. And finally, visualization, which is section 6. Well, the models in this section are all visual, and this is for, if you watched my previous video from about climate models, the development of them. The models in that section were all visual, and this has a reason. Visuals are easier for humans to comprehend, and compared to a collection of data, which is generally very large, the computer helps to compress all of this data. Colors, shapes, lines, and many other techniques can be used to make the visual more comprehensible. The visual here, from the software on the website wordle.net, presents all of the words from a blog post on the International Baccalaureate website relating to IB position papers. The bigger the words are, the more often they are used. As you can see, IB was the most used in this specific post. This visual is useful because if it were shown in a table, it would not be nearly as comprehensible, nor appealing to the eye, as there would just be words with maybe how often they were used. And but in this way it is much more appealing to the eye, obviously. So, my sources, here they are, and adios, gracias.